Okay, this is Mr. Anderson for Math 130 Statistics. We're going to look at sample spaces and probability. We're also going to spend today looking at OR probabilities. That's going to be our goal for today, to look at the probability of getting this or that. And that basically is going to boil down to things that are mutually exclusive or not mutually exclusive. And we're going to be talking a lot about dice and cards today. So, what is a probability experiment? It's a chance process that leads to well-defined results called outcomes. So we're going to look at ways that we can make outcomes by rolling dice, picking cards, and perhaps flipping coins. And an outcome is the result of a single trial. Of an experiment. So when we look at the outcomes, we're looking at every single result from rolling a die, flipping a coin, or picking a card. And a sample space is an organized list of all outcomes. So what I've done here is on the worksheet, I actually have some ways to organize a couple things. For example, rolling two dice. You'll notice that the first die is at the top and the second die is at the bottom, or on the column here. This would be if you rolled two ones, you'd have 1, 1, and that would add up to 2. Also, if a 1 was rolled on the first dice and a 2 was rolled on the second, this would be 1, 2, and this would add up to 3. Now, instead of me filling this entire thing out, I can just jump around a little bit and let you think about this. If I was going to go from 4 on the first die and 3 on the second die, this would be 4 and 3, and that would add up to 7. And if I was going to go all the way to the end, I would have 6 and 6, which would add up to 12. Now, I've made some half sheets, and the half sheets are going to have all of this filled in, and you can download those off of my Moodle site. Those files will be available to you. A filled out version of that table will look like this. And I will also have below it the card chart. So you can kind of see that all of the, whoops, get that into focus here. You can see that all of the sums are listed next to each die. You'll also notice that 7 is the most popular sum on this sample space. This sample space has 36 total outcomes because each die has 6 separate digits. And 6 times 6 is 36. That's simple multiplication counting. Now for cards, on the other hand, this would be the 2 of hearts, the 3 of hearts, the 4 of hearts, and if we go all the way to the end, we'd have the ace of hearts. And I'm just keeping this consistent with the table above it where my column would get to go first here. And so this would also be filled out like so. And you will notice that there are 4 cards for each number of each different suit. And you'd also have pretty much hearts, diamonds, spades, and clubs. So 13 of each of these different suits and 4 of each kind of card, no jokers, which gives me a total of 52 total in my sample space. And again, this is going to be available on my Moodle site right here for you to download and use on your homework, so you're not having to flip back and forth, but it is a good exercise to fill out these charts in the meantime. Okay, now another way to have an organized list of all the outcomes is to use a tree diagram. Now I will show you flipping a coin 3 times using a tree diagram. So the first coin would be heads or tails. And the second coin would be branching off from each of these heads, tails, heads, tails. And that would be the second coin. And then the third coin would be another set of branches, because each of those would branch off twice, heads, tails, heads, tails, heads, tails, and heads, tails. So this is a tree diagram of flipping a coin 3 times. So this outcome would be heads, 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 and this would be heads, heads, tails. And to go down, heads, tails, heads, heads, tails, 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 heads, heads, tails, heads, tails, 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 heads, and then finally tails, tails, tails. When you flip a coin 3 times, each coin has 2 outcomes. So the 2, 4, and 8 would be the simple multiplication of, how many samples, how many outcomes you had, and then how many different paths you could travel down afterwards. So if you think about it quickly here, if you had to roll a die and then flip a coin, rolling a die would have 6 outcomes, and flipping a coin would have 2 outcomes. So if you wanted to roll a die and flip a coin and look at all the different possibilities, the 6 outcomes from the die and the 2 outcomes from the coin, that would give you a total of 12. Because you'd have 6 options here, and then each of those would branch off heads, tails, so on and so forth. And that would give you 1H, 1T, 2H, 2T, 3H, 3T, 4H, 4T, and 5H, 5T. I'm running out of room here. 6H and 6T. Now that's another example. One example that kind of gets into the future is choosing things in order. So let's say we're going to choose 3 sodas. And this is to show you that sometimes we can't just simply multiply one set of outcomes by the other set of outcomes to figure out how big our sample space is. Let's say we choose 3 sodas, and we're going to give the sodas the name Soda A, Soda B, and Soda C. Now let's say that the sodas will not be replaced after you choose them. So once you choose A, you really only have 2 choices left, and that's B and C. And once you choose B, you only have 2 choices left here. Those choices are A and C. And you can see that once we pick C, if that was your first choice, then B and A would be the only ones left. This means, too, that now you have these options here. A, B would then, the only can left would be C. A, C, the only can left would be B. B, A, the only can left would be C. This would be A. This would be A. And this would be B. So you can see that those cans sorted in order would be ABC, ACB, BAC, BCA, CBA, and CAB. Now this is going to bring up, for the next lesson, dealing with something called factorial. And factorial is when you take a number and multiply by its choices. And I accidentally wrote down 6. What I meant to write down is 3 factorial, because there were 3 different cans in this item. And if you choose 3, then you would have 2 choices in the end, and then you'd have 1, which would give you 6 choices. Or 3 times 2 times 1 equals 6. And we're going to talk more about that in the next video for the next lesson. Now, let's talk about a simple event. A simple event is when you're looking for just one simple thing. Look for one result. So if you're rolling a die and you need to get a 5, that's a simple event because you're just looking for the one result. Now a compound event is when you're looking for more than one result. So look for more than one result. And this would be, for example, if you're playing a game of cards and you need maybe more than one card to win. Like let's say you have 4 cards to make a straight, so you're looking for one card on either end, and so that would mean that you're looking for just more than one specific card out of that deck. Okay, on the second page. Got a couple of vocabulary terms here. I just want to kind of burn through it. First of all, we're going to talk about classical probability. What we're going to do is we're going to use sample spaces to determine the mathematical probability, and all outcomes are equally likely. When we do classical probability, we're going to take a look at these simple things of rolling dice, flipping cards, looking at probabilities, and we're going to assume that each type of a result is going to have the same likeliness. So it's not going to be easier to get a heart than it is a diamond. That, of course, means that each card is easy to pull. I guess if you remove some of the diamonds or hearts, that would change the probability. Now, here's the book's way of talking about the probability of an event. It's the number of outcomes in your event that you want to have happen, divided by the number of outcomes in the sample space. Now, the way I've simplified it, it's kind of like what you want over the number of possibilities that you can actually get. So that right there is probably an easier way to say it. Like, you would want the one lottery ticket to win, but there are lots of possibilities for those numbers to come up in different order, and that means that your chances of winning the lottery are one out of a lot, and we're going to figure out some of those in our next worksheet. Now, let's talk about the rounding rule for decimals. You're going to, for probabilities, round to 3 decimals, and I'm going to show you some of that right here. Rounding with these probabilities to 3 decimals, if I give you a probability that's 0.084, that's acceptable, because that's rounded to 3 decimals, and if you wanted to turn that into a percent, that'd be 8.4%, or rounded correctly, 8%. Now, if I gave you 4 decimals, like 0.8239, you would have to round this to the 3rd decimal or the 1,000th, and so this would be 824 thousandths, or 82.4%, or rounding it to 82%. Now, there are some situations where you're not going to be able to round to just 3 decimals. In some of the most extreme cases, you're going to have a lot of zeros. So I've written 7 zeros and then 741. Okay, so I have more than 3 decimal places, but if I round to the 3rd decimal place, it'd be a 0. Well, in this situation where you have more than the 1,000th place, you're going to round to that first non-zero number. So this would be rounded to 7 zeros and a 7. So that is what you would round to. If that number after it was a 5 or above, you would move that to an 8. Okay, and then we're going to move to the probability continuum. The probability continuum goes from 0% to 100%, and in the middle is 50%. In decimals, that would be 0.5 and 1. So probability continuum is anywhere between 0 and 1. So your probability will never be below 0% and never be above 100%. Other things, this is basically impossible. If you have a 0 chance, this is going to be an impossible probability. This is all unlikely, and this is very likely, and then this is definite. 100% chance of happening is a definite situation. All right, now, the law of large numbers. This is a little bit modified to make this kind of easy to swallow. This is eventually the probabilities come true. Now, what's important about that is if you are playing at a casino, and I will bet that most of the time when you play at a casino, your chances of winning are below 50%. Eventually, the probabilities come true. So if you do win at a casino, which maybe was a little bit unlikely, if you keep playing at the casino, eventually the probabilities will come true and you will walk home losing your money. Because even if the casino has a 51% chance to win and you have a 49% chance to win, the probabilities will come true and you will end up giving your money back to them slightly faster than they will to you. But I will be very interested to see what the actual probabilities of winning some of those games are, and eventually, as long as you stay there, you will lose your money. This is also kind of a word of warning. Look out for subjective probability. Subjective probability is based on guesses, and even estimated guesses, which are still guesses, opinions, or inexact info. The book spends about a paragraph or two talking about this, and there is subjective probability, but if it's just not scientific probability, you're probably best not using it. And now we get to the meat of today's lesson, which is the laws of getting an A or a B. That's important because we want to take a look at what a mutually exclusive event is. This is going to pretty much decide one of the two rules we're going to use for our problem here. Mutually exclusive events have no interaction. No interaction at all. All right. And this is not the same thing as independent. I want to just purely define mutually exclusive events as one that doesn't have interaction with the other. So, for example, this is a quick example. If I decided in one hand to roll a die, and then in the other hand at the same time flip a coin, and there's not going to be any collision of said item to the other, this is an example of mutually exclusive events. Now, another we can talk a lot about mutually exclusive events when we get into the cards and dice, but I want you to look at each specific case and ask yourself, was there any interaction? Now, the good news is, if two events are mutually exclusive, then we can do a very simple calculation to figure out the odds of it actually happening. So, if mutually exclusive, and I'm sorry to abbreviate this here, if mutually exclusive, then we can take the probability of A and add the probability of B together to get our results. And that will tell us our chances of winning. So, for example, if we wanted to find out the probability of drawing a heart or a diamond out of a deck of cards. So if we wanted to draw a heart or a diamond out of that deck of cards, we know there are 13 hearts and 13 diamonds, and there are no overlaps. So that would be 1352 plus 1352 is a total of 26 over 52, or 1/2. And that would tell us, that since there were no overlaps between hearts and diamonds, then we have our total odds of that happening. Half the deck is hearts or diamonds, so your chances of getting a heart or a diamond is 1/2. Now, here's the hard one. If it's not mutually exclusive, if there is overlap, we have to use this formula. We have to take the probability of A plus the probability of B, and then we have to subtract the probability of A and B. We've got to subtract that. And the reason why we have to subtract it is because there's overlap in the two data sets. So let's take a look at this example. What if I want a probability of drawing a heart or an ace? So it can be a heart, any heart in the deck, or it can be an ace of any suit. That means an ace of heart, diamond, club, or spades. Well, the probability of drawing the heart, oops, kind of didn't want to write that. The probability of drawing the heart is going to be 13 out of 52. And the probability of drawing the ace, which is event B, is 4 out of 52. But then I have to subtract an overlap. Is there a heart and an ace that happens to be in the same group? And there is. So what I have to do is subtract that overlap of P and B, which is 1 over 52. So my answer is going to be 13 plus 4 minus 1, or 12 plus 4, and that is going to be 16 over 52. And that 16 over 52 can be reduced, and I want to show you kind of a cool way to reduce on your calculator, and I know you could probably just, easily divide by 2 or 4 or 8 or the numbers there. But one of the easier ways when you get to the bigger numbers and you take the 16/52nd, what you can do is you can hit the math button and then the fraction button, and that will simplify that fraction toot sweet. And the answer is 4/13. Now again, I really don't expect you to do that for some of the more simple fractions that you have in front of you, but this will save you time when we get to some of the answers on the back. So 4/13 is going to be the odds of you pulling the heart or the ace. Alright, so with that in mind, let's go to the last page. Okay, what I'd like you to do is I'd like you to pause the YouTube video, and I would like you to try these out, and I want you to try them this way. Using the dice chart that you have, and maybe got it off the Moodle page or finished it on page 1, I'd like you to try to do the sum of 7. Like, how many 7s are there on the chart? I'll do this one with you here. So there are 6 of them out of 36, which can be reduced to 1/6, which then has a decimal equivalent. And I think I want you to get the decimal equivalents here to test your rounding skills. And you can go to any calculator and go 1 divided by 6, and then round it to the thousandth, which is 0.167 or 16.7%. So pause the YouTube video and try to do the rest of this whole page, and I will explain the answers once you unpause it. Okay, you should have now unpaused all your video, and here is the answer key. For the sum of 2, there was only one of them on the chart, so 1 out of 36 is 0.028 or 28 thousandths, around 3%. An even sum, well, there are 18 out of 36 that are even, which is 1/2 or 50%, or 5/10. The sum of 11, there's 2 of them on the chart. So that's 2/36 or 1/8, which is the 1/18, which is a decimal equivalent of 56 thousandths, 5.6% or 6% rounded. Okay, having at least 1 3. Now, what's interesting about that is you should look at all the numbers that have 3s in them. Now, I'll notice that this whole column has at least 1 3, and this whole column, this whole row has 1 3 in it. So we have a total of 6 and 6, but we're going to subtract the overlap, so we have a total of 11. So there's my 11 out of 36, which is not reducible to about 30%, 301 thousandths. Okay, so now we have probability of doubles. There were 6 out of 36 there, which is 1/6 or 167 thousandths. Okay, 7 or an 11. Well, that's an interesting one, because you'll notice that above here I have the probability of the sum of 7, sum of 11. Since they're mutually exclusive, I can just add those up. So 6/36 plus 2/36 is 8/36, which is reducible to 2/9 or 22.2%, 222 thousandths rounded. The doubles, or a sum of 5, these are another set of mutually exclusive events. Probability of doubles is 6 out of 36, because there are 6 of them. And the sum of 5 is 4 out of 36, but there are no sums of 5 that are doubles, so this is mutually exclusive. You can add that up to make 10 out of 36 reducible to 5/18, or 27.8%, 278 thousandths, or 28% rounded. Alright, now here's the fun one. Doubles or a sum of 6. Now this is not mutually exclusive, because doubles was 6 out of 36. A sum of 6, there were, on the chart here, if you take a look, your doubles were going down the diagonal here. So we have this one, this one, this one. All of these are doubles. And then we have our sums of 6s, which goes up here, but notice there's an overlap there. So we have 1, 2, 3, 4, 5, 6 doubles, 1, 2, 3, 4, 5 sums of 6, and 1 overlap. So 6 out of 36 for my doubles. We've got 5 out of 36 for my sums of 6s. And then 1, we're going to subtract, sorry, I made a plus negative there, 1 out of 36 for my overlap, which makes a total of 10 out of 36, which breaks it down to 5/18 or 278 thousandths. Now, another way you could do that, if you're having trouble with the formula, is to just count the circles. And you'll notice I have 10 circles there. Just don't double count this one to make 11. Now here's a Venn diagram. The Venn diagram has, on the left-hand side here, all the doubles you can get, 1, 1, 2, 2, 4, 4, 5, 5, and 6, 6. And over here on the right, we have sums of 6s, 1 and 5, 5 and 1, 4 and 2, 2 and 4. But you'll notice here that they both contain 3 and 3. The Venn diagram shows that this right here is the intersection of all the doubles and the sums of 6. So this is why this is not mutually exclusive. Mutually exclusive groups would have two Venn diagram circles not connected to each other, like separate circles. Alright, now this drawing an ace. An ace, 4 out of 32, 1/13th, or about 8%. Getting a club is about a fourth. It's 25%, because there's a quarter of the cards are clubs. Drawing the ace of clubs, this is one card. This is a 2% chance of happening, 1 out of 52. Now this is the complement of getting the ace of clubs, which is 51 over 52. So really the complement is saying not the event, which is given by this symbol, E bar. Now if you take the event and add the E bar, you'll get to 100%. Or 100% minus your complement gives you the actual event. So the complement is saying it's not going to happen. So this is, I want the ace of clubs. The complement of that event is not wanting the ace of clubs. Okay, getting a heart or an ace. Now the heart or an ace, this right here is a... the heart or an ace, this is the problem that we did before right there. So we talked about 13 plus 3, which gives you 16 over 52, 4/13ths. And we did this on the previous page, but here's the percentage right there, almost 31%. Getting 3 of clubs or a diamond, these are mutually exclusive. So the 3 club is 1/52nd. The diamond is 13/52nd, which is 14 over 52. Reducible to 7/26 and 269 thousandths. Okay, and then here we have 19 over, this is the fun one here. This is getting a heart, an ace, or a 9. Let's go take a look at the chart here. A heart. Okay, if I want a heart, I'm going to choose pretty much everything on this list here. There's the heart. Right there. I'm turning that sideways so you can see that in there. Now I either want an ace or a 9. So what's interesting about this is I'm going to add up all 13 plus 4 minus 1 minus 1. Now obviously an easier way to do that, just count all the circled numbers right there. But to show this out in one last step, how I got 19, that's 13/52 plus 4/52 plus 4/52 minus 1/52 minus 1/52. 1 over 52. Sorry about that. Made it sound like I was saying 152. So 13 plus 4 minus 1 is 19 over 52, which is about 37%. Okay, so there's your homework. Now, in the next video, I will give you a little bit of a hint to help you out with some of the homework problems or the 4th page of the worksheet.